Good morning and good afternoon, everyone. My name is Abdullah Ibrahim and I represent Addisol, a company dedicated to advancing additive manufacturing and testing solutions with the aim to empower industries, universities, and R&D institutions worldwide with the tools, knowledge, and support needed to accelerate innovation and achieve breakthrough results. Right now, I am connecting with you from London, where the temperature is about 19 degrees Celsius, but the wind is making it feel like 9. This webinar is held in collaboration with Paanduv Applications. And the title of this webinar is Advancing Additive Manufacturing Solutions in the Middle East, with a specific focus on Paanduv's proprietary software, AM PravaH. Over the next 20 or so minutes, I will share how Addisol's work supports innovation in the Middle East and discuss how advanced simulation tools like AM PravaH are essential for the future of manufacturing. So, Addisol. Who are we? Well, at Addisol, we bring together years of combined experience in additive manufacturing, testing, and turnkey lab solutions. We don't just sell machines, we deliver end-to-end solutions. For example, in hardware, we offer our clients a large range of dedicated solutions from both desktop and industrial 3D printers to recycling machines for both polymer and metal recycling, and then to add on to this, filament makers to basically finish the upcycling process, all the way to finishing machines like sandblasting, etc. In software, we now offer advanced simulation tools with our partnership with Paanduv, and especially their proprietary AM PravaH, which is a comprehensive software that can dictate workflows and save our clients both time and money. At the same time, we also offer contract services such as custom manufacturing, 3D printing, all the way from designing to prototyping, material testing services, and trainings that can push our clients to success. Our printing facilities deal with polymers, metals, and all forms of composites. Finally, we also take huge pride in our advanced laboratory setups. In recent years, we have set up fully integrated solutions for geotechnical as well as material testing labs for universities, R&D centers, and a lot of industrial clients. In short, Addisol is a one-stop shop for all things AM related. So, our areas of operation in the Middle East include Qatar, Saudi Arabia, UAE, Kuwait, Oman, Bahrain, Syria, and Jordan. We are partnered with several industry leaders, including Paanduv, WTech, QuantAI, Amplitudo, and Kson. Our partners are Addisol's backbone, and they help us bring state-of-the-art solutions to our customers' doorsteps. So, what kind of impact has Addisol had in the Middle East? Well, we've had quite a direct impact on research and industry, specifically in the Middle East. As I mentioned before, we've helped universities and R&D centers set up facilities from scratch, but we've also helped our clients meet their sustainability goals while upcycling. This includes providing twin screw extruders that can mix multiple recycled polymers and then convert them into pellets, filament makers that can convert these pellets into usable FDM filament, and also rheological material testing machines that can determine the printability of these recycled filaments. At the same time, we also provide powder atomizers that allow a similar recyclability for metals. So, the capabilities and services available at Addisol. Our goal has always been to assist our clients from concept all the way to the finished part. Our core capabilities include 3D printing solutions such as SLM, binder jetting, polymer extrusion, composites, CFC technology, as well as direct energy deposition. Material testing equipment such as universal testing machines, dynamic mechanic analyzers, hardness testers, fatigue testing machines, all the works. We also provide geotechnical testing machines like triaxial, consolidation, and solid mechanic equipment. As I mentioned before, we also offer contract services such as on-demand 3D printing, whether small or large-scale assemblies, as well as finishing, mechanical testing for client projects. Basically, our team of design engineers is proficient in reverse engineering parts for metal 3D printing, as well as designing bespoke solutions for our clients. We cover the full workflow, from design and simulation to printing, post-processing, including finishing and painting, all the way to quality testing to ensure that parts are ready for critical applications. Finally, we also help our clients adhere to compliance certifications. For example, recently we helped one service center get a DNV certification. Now, as I mentioned before, we are expert in turnkey solutions and handling complex projects. We take pride in turning ideas into tangible products. One such example is our recent project for Lakhvia, National Guard of Qatar, which was the first 3D printed helicopter in the Gulf region. So Lakhvia came to us looking for a solution to allow simulation of rappelling exercises for troop training purposes. Specifically, they wanted to cantilever a 2-scale model of a helicopter and then install it within the top floors of this building. It seemed complex, but our team decided to take up the challenge. So we started with the design. As you can see on the top left, we modeled the building as well as the helicopter first in order to draft a clear plan of action. Then we sectioned different parts of the helicopter's body, as you can see in the top right picture. And then we also realized that having the whole body 3D printed would be neither feasible nor safe. So instead, we decided to machine and fabricate some parts of the helicopter. So the red parts that you see in the bottom left picture are 3D printed, while the blue ones are fabricated through sheet metal fabrication. And of course, to make such a large-scale model, we would need a proper frame and support, for which we designed a metal bar frame, as well as the beams that would cantilever the helicopter and hold it in place. You can see that in the middle picture in the second row. And thus, after designing, began the printing process. Using our largest 3D printer from Sweden, we began printing the nose as well as the body of the helicopter. And then here, you can see the fabricated support structure or the frame, all of which was fabricated in our facilities in Qatar by our own team of engineers. Zero outsourcing. And this video is also going to give you an idea of the size of this project and showcase how our team dealt with the difficult task of managing so heavy an assembly. And the frame was also assembled with a safety hatch integrated into it. You can also see the initial phases of painting and finishing in this video. And then this is the beam structure that would have held the entire assembly and frame together with the concrete slab. Again, fabricated in our facility by our own engineers. Some more finishing, specifically of the backside of the helicopter's body, where the engine exhaust can also be seen. And bit by bit, you can see the assembly coming together. This is the front side, the nose of the helicopter. And thus began the installation process. This project was a task and a half, but after 6 months with a team of around 20 engineers, 5 PhD holders, and hundreds of skilled workers and technicians, all of them a part of Addisol's teams, we were able to deliver the final result. And this is just one of our most recent ventures in the Middle East. Addisol prides itself on its ability to undertake such daunting projects, whether it's large-scale assemblies like this one, or a simple reverse engineering task that can help drive our customers to success. We can do it all. A true one-stop shop for all your needs. So that's basically a summary of our service stack. Now let's zoom in into a technical place where small choices have big costs, metal 3D printing, and more specifically why simulation is the lever for getting things right the first time. So why does simulation matter in metal 3D printing? Simply to reduce defects, save time, and optimize performance. All workflows aim to meet this specific criteria. When it comes to defects, 3D printing process of metals is a process riddled with them. The process involves complex physical phenomena occurring across multiple time and length scales. The types of defects include porosity, which can create weak spots and eventually cause cracks. And then these cracks are also closely related to residual stresses and incomplete fusion. Another common type of defect is the balling phenomena, where liquid metal solidifies into sapphire under the action of surface tension, and this eventually leads to a negative impact on the powder quality of the next layer. These are just some of the process defects that the metal AM process involves. Avoiding such catastrophic defects, though, is essential for team leaders, especially when it comes to the ideology of first time right. Every hour on the machine and every kilo of powder is cash, pure cash. Simulation lets us test ideas on a screen first, so we avoid failed builds and we accelerate approvals. The outcome that we are after is simple: first time right, more often, and a faster path from concept to qualified part. This stands out even more when we consider a process like metal AM, where raw material and process costs can build up rapidly. Repeated work is a liability and it can absolutely ruin workflows. Now, what do team leaders care about? So, how do we de-risk new parts and materials? How do we shorten time to market? And how do we standardize process knowledge across teams? These are the questions that we hear the most often from R&D, production teams, and quality assurance teams. The right simulation approach tackles all three of these: de-risking, speed, and institutionalization of the best practice. And the answer to all these questions lies in selecting the right simulation tool. So typically, metal AM simulation models work at multiple scales: the micro, the meso, and the macro. Now, going backwards, for the macro scale simulation, FEM approach has been widely used by many models. At the meso scale, CFD, SPH, and the lattice-Boltzmann methods are used to analyze fluid flow in the melt pool. And at the micro scale, phase field, Monte Carlo models are used to analyze grains, nucleation, and voids. But due to the large number of parameters and the complex multi-scale physics involved in this AM process, simulating an entire part from end to finish is generally not computationally feasible. Nor is there any simulation tool that can conduct a simulation at each of these scales combined. Enter AM PravaH. AM PravaH unifies micro, meso, and macro in one physics-first engine. It couples melt pool CFD, powder track dynamics, and microstructure with part-scale LPBF and WLAM builds, so you can design the process, not just check it. Let's put a spotlight on AM PravaH, go a bit deeper. So, unlike generic tools, AM PravaH is built from the ground up for AM physics, and then it is sped up with AI-assisted parameter search, as well as using parallel processing to move quickly from an idea to a printable window. Using the proprietary physics model, AM PravaH can simulate from the micro scale, such as microstructure evolution, to the meso scale, which can be seen here with the simulated powder bed in the second visual, all the way to macro scale full part evolution, as shown in this last visual. So, just summarizing, what is AM PravaH? Well, and what does it do? AM PravaH covers the processes that most teams run, LPBF, along with wire-based DED. And it doesn't just sit in the corner as a science project. Rather, it's built for day-to-day decision making, checking recipes, comparing scan and bead strategies, and flagging risks before you book a machine. In this last GIF, you can see AM PravaH successfully capturing and highlighting keyhole porosity, a defect that can cause catastrophic part failure. Now, where does this pay off? Well, less rework means fewer wasted resources, as well as less surprises for planning and sales. It also gives production teams clear and better documented recipes so that programs can scale smoothly, allowing cleaner handoff from R&D to production. You can integrate AM PravaH into your existing CAD and CAM machines, and using its physics engine, you can run quick what-ifs before even scheduling a single build. Using the power of simulation with AM PravaH, you can determine the best recipes or parameters, and then take away lessons that can then be used by AM PravaH's AI-powered Q mode to give you the best parameter combinations for any given scenario. So don't just predict the outcome, design the process that creates it. AM PravaH's process-aware simulations can show you how your choices can cause defects, and then you can decide how to overcome them. Many simulation tools can report outcomes, but AM PravaH stands out by helping you design the process that creates these outcomes. You'll see that in the demo and how changing settings shifts risks before you even waste any precious resources. So, really quick, what do LPBF teams get? Well, for LPBF, AM PravaH gives us confidence on the core knobs: laser power, scan speed, hatch, layer thickness, and beam shape. And it does this by showing how they drive the melt pool specifically, as you can see in the visual on the right. In practice, we are always looking for a stable melt pool footprint, which involves its depth and its width. And we want this melt pool to fully fuse tracks without forming a deep keyhole. The software flags certain regimes linked to keyhole porosity, linked to lack of fusion, and basically also all other types of defects like balling on thin features and overhangs. And because the powder quality is Model 2, including non-spherical particles and packing, you can see how rough or sparse layers increase the risk of the before the laser ever moves. On top of that, we can also test different beam profile shapes to widen or stabilize the melt pool on sensitive geometries, and run multi-layer, multi-track windows to check if a recipe can stay healthy as heat accumulates. The net result of all of this technicality basically is faster approvals for thin walls and new allies, fewer scrap builds, and just a much cleaner sign-off from R&D to production. So in this video, you can see a higher fidelity 4-layer simulation. Less layers, but this video really showcases the fidelity and depth of AM PravaH's physics-based simulations. So you'll notice that within the simulation, the software captures an interlayer lack of fusion, and the simulation identifies these defects caused by low power laser power or high scan speeds, could be either, and then offers crucial insights into the process optimization. Now, after the third layer, you'll also notice stable patterns. By the third layer, stable deposition patterns are observed, indicating consistent layer buildup and enhanced process stability. Now, what about wire DED? What do you get for your team? Well, on the right, you see WLAM, wire feeding into a laser-made melt pool. The top image is a simulation view from AM PravaH, and below it is the high-speed camera from a lab run. The point is simple. What we see on screen mirrors what happens on the cell. And why does that matter? Well, first, it gives us predictable bead stacks on real geometries. We can preview bead height, width, and overlap along walls and corners, as well as curves. And thus, the stack builds evenly instead of wandering. Second, less tuning on the cell, basically more stable runs. Before we book time, we try a few recipes, laser power, speed, spot size, wire feed, and also the angle, and then we pick the ones that keep the pool smooth and the wire joining and make sure the wire joins cleanly. And that takes the stop and start guesswork out of your setup and basically just shortens the bring up on the robot. And finally, the outcome you care about downstream, which is basically better machining allowables and better finishing plans. When bead height and width are consistent, your programmers can hold a tighter allowance, tool paths are going to be cleaner, and you don't have to chase surprises after roughing. Now, where does Addisol come into all of this? So you're not just buying a black box. You're basically going to be getting a rollout. Addisol is going to be your partner. It's going to handle onboarding and training, tailored to your machines, your materials, and your QA requirements. We map PravaH's outputs to your qualification artifacts. For example, defect risk maps, track parameter windows, and microstructure indicators that can support internal reviews. If you need it, we can wrap this with on-demand printing and mechanical testing, tensile, hardness, fatigue. So you have a single partner, basically, from simulation all the way through verification. The goal is to shorten your learning curve and lock a repeatable way of working that your team can own. So to keep this session focused on customers and outcomes, we are going to hand over to the AM PravaH team for a live demo. You will see the LPBF view of melt pool dynamics and the defect indicators we mentioned, plus wire DED bead predictions and how parameter sweeps find a stable window. As you watch, think about one upcoming part or one material that you'd like to de-risk. And then we're going to use the Q&A session right after to shape a quick pilot around it, including licensing and support options. Thank you very much, and over to the AM PravaH team.
Hello everyone, I am Pradeep Das, a material scientist at Paanduv Applications, and today in this presentation I will be discussing about the computational potentials of the software that we have developed. This particular session is for the collaboration between Addisol and Paanduv Applications. I will be talking about one of our flagship products, that is AM PravaH, that is designed for an end-to-end additive manufacturing solution for the entire workflow. where we will be simulating the processes across different length scales. Starting with about the introduction about us. This particular software is a brainchild of Mr. Advait Gupta, who has been the lead developer of AM PravaH. And at Paanduv Applications, we are based in India. And at Paanduv Applications, we will be dealing with the computational scientific solutions provided for multiple problems that are dependent on CFD and different aspects. So in the context of AM PravaH, I would like to highlight about the different length scales that are actually operable in case of an entire workflow. So starting with the micron to Armstrong's length scale, what we can see here that the length scale where we are actually operating into relies between somewhere between micron scale to beyond millimeter scale. So these are the uh, area where we will be operating. Our simulation software solutions are delivered for across these different length scales, that is starting from the micron scale to the beyond millimeter scale. So with AM PravaH, we tend to work on three fundamental additive manufacturing processes, which is laser powder bed fusion and wire based direct energy deposition techniques, which includes wire laser DD and wire arc DD processes. Starting with some of the validations of the particular software, what we have observed and what we have uh, reached so far is that we have validated the synchrotron X-ray images and tend to understand the subtle physics of this particular problem. And with our simulation tools, without performing even the experimental tools, and we can have an idea about how this particular process governed by complex phenomena is actually operating in. You can clearly see from these results that how accurately the particular phenomena is captured, considering the different manifolds of this particular process, which includes the defect formations and tending to different melt pool profiles. That's what we are doing for the melt pool dynamic simulations. Some other subtle features that we would be solving in our multi-phase multi-physics software solutions, it includes the laser, changing the different laser beam profiles so that we can have different thermal histories and we can generate the different sorts of material properties. And that's what we tend to do with the laser powder interactions, the capture the complex phenomena like the Marangoni convections, also the transient heat treatment and transient temperature profiles that are evolved during the entire process. With that in aid, I would like to demonstrate certain defects that we have captured quite successfully, and that involves the deep physics that is within the formation of these sorts of defects in these innovative processes. We are not restricted to a single layer process. We have extended ourselves to multi-layer processes as well, capturing the all the subtleties in the of the processes itself. For the microstructure, it is one of our interesting modules. What we have observed that the process parameters govern the microstructure formation, which eventually leads to the formation of different properties. So this is what you can see here, and how exquisitely we have captured those areas which are left over in the experimental. That's how we reduce the reliance of the experimental exhaustion for the researchers across the globe and for the engineers who have been working in this particular field. We use the in parallel the four-phase multi-phase problems along with the different Monte Carlo based models to model this microstructure solution. Here is one of the another validation that you can see that we have accurately captured the deviations of the grain sizes as well, wherein you can see that we have validated our results against the experimental EBSD analysis. We are modeling and simulating the two different wire DED based processes, which is wire laser DED processes, and wire arc additive manufacturing processes. These processes includes different material deposition modes and covering different defects that are generated in these sorts of processes. We can also see here as well the close proximity between the experimental results and the simulation results, and we have obtained a very good fit between these two. In a nutshell, to cover the benefits of AM PravaH, we place ourselves as an end-to-end simulation solution for the additive manufacturing processes, ranging from powder preparation to part scale simulations or the bulk simulations. We have seen that using such a physics informed software, you can cut down the operational cost by about 67%. Typically for different material innovation and part scale qualifications, it can reduce the costs further. Also, it reduces the reliance upon the extensive characterizations and experimental trials that engineers and researchers tend to do in building a component. We also immerse ourselves as a virtual twin for the different additive manufacturing processes, and therefore we place ourselves as a physics informed simulation tool that can solve different uh, additive manufacturing problems, and it also improves the efficacy of the entire workflow. So we equip ourselves with a simple GUI, and it's a very user friendly interface, and also we take up different temperature dependent thermophysical properties that will enable us to capture the subtleties such as different thermodynamic actions in a different length scales. Also, we come up with a integrated material database, and also we can customize the different other variables such as the shielding gas, the powder distribution, and the scan patterns. We can have different hatches, different strategies that are included in our GUI. Also, it enables vary the process parameters drastically, starting from, let's say, the laser parameters, the scan parameters, and different other aspects. Also, with the aid of such software, we are also simulating the other parameters as well, that is the different computational parameters. And also we augment ourselves with AI based models that the database that we generate, and aligning with the data that is available in the literatures, and we combine that to come up, and we further optimize the entire process flows. We also reduce the reliance of human efforts by including another module, that is Q, wherein you can add up different simulations and you just need to run the software. So that's all from my end. You can know more about us and more about our softwares and how it operates using the description links in the description below. And that's all from my end. Thank you so much.